going with that, we know that for every 2 generations, or if you have 2 individuals between them, they have about 3 beneficial mutations. In the last 10,000 years since the rise of agriculture, there have been, in a single parent-to-daughter line, and in this case, daughter could mean guys too. We're just talking a direct line of individuals. You would have about 1,000 beneficial mutations. Mutations like the CCR5 mutation, which provides immunity against the AIDS virus in homozygous individuals. There's about 10,000 or so mutations over the last 100,000 years in that same single line family. Or since the divergence of humans and chimpanzees, we're talking about 600,000 mutations in that single line descent. Of course, humans aren't a single line descent species. We have multiple descendants. And if you take a population size that averages about 1 million or so descendants per generation, and an average human generation is actually about 15 years, may seem a little bit different nowadays because, laws pretty much limit people from breeding, or at least we're supposed to limit people from breeding until after the age of 18. But in general, with most humans, it's about 15 that they're capable of beginning to breed. So if you do the math on that, over the last 6 million years, there have been a potential of 60 billion beneficial mutations. That's 10 times, roughly 10 times, the number of base pairs in our genome. So can beneficial mutations occur? Yes, they certainly can. Can enough of them have occurred to allow for the divergence between chimpanzees and humans? Most certainly. And again, these are just generalized figures. The actual figures are different. Most of these beneficial mutations are not retained. Some of them are converted back due to a second mutation affecting the same part of the genome. Some of them are lost through accident. A baby may have a beneficial mutation, but that baby's killed by or being dropped by its parents or something. Entire families can be wiped out by disease or by war. So the truth is, even if only 100,000th of these generations survive, of these beneficial mutations survived, that would explain the difference between humans and chimps genetically, and more than likely more than that actually survived. So that said, let's continue on. We have the next one, number 6. Chances random mutation is both beneficial and appears at the same time needed. Well, to answer this one, you need to have a significant amount of data regarding the specific mutations that occurred and the selective pressures at the time they've occurred. Of course, this isn't how evolution works. It doesn't try to mutate for a specific occasion. Many beneficial mutations are neutral or even slightly deleterious under certain selective pressures, and only become beneficial after selective pressures have changed. This is known as pre-adaptation. It's well known. It's observed. And I think I have what I wrote down here, I think I have an example of that later, but maybe not. Oh, right here it is. It's actually under number 7, so let me read number 7. Chances of beneficial mutation being passed on. Is better than the chance of deleterious mutations or neutral mutations. Well, maybe not mutual mutations. Mutations. It's late, I'm having trouble speaking, I'm sorry. It's less than 100%, but roughly greater than 80% that a beneficial mutation will be passed on to the next generation. Give or take, it might be as low as 60%, but I'm going on a memory here. I couldn't actually find the paper I'd read on this, so let's just go ahead and assume 60%. Let's lowball it even further. The actual amount depends on the beneficial mutation and the selective pressures in the environment. As an example, consider bacteria. If you have a bacterium that has a mutation allowing it to survive a specific antibiotic, under normal conditions, there is no difference in reproductive success between it and its peers. However, when that antibiotic is present, that bacteria's reproductive success will be 100% better than its peers. So it depends on the environment, and it depends on the selective pressures. Always keep that in mind when you're talking about deleterious, beneficial, or neutral mutations. You can't speak of those. You can't speak on mutations without considering the environment they're in. Now, here's an interesting one, and I think this goes to show MackQuigley's lack of understanding in regards to genetics. What are the chances of finding a mate with the same mutation? As if it's necessary for mutations to be homozygous all the time. The truth is that with genetics you have dominance, recessive, and co-expressive genes, or co-expressing genes. I have blue eyes, so I have 2 recessive genes for blue eyes. My dad had blue eyes. He also had 2 recessive genes for blue eyes. My mom has brown eyes. She had 1 of each. 1 recessive gene for blue eyes and a dominant gene for brown. Are select sections of genes. Now, obviously this means that you do not have to have an individual with the same mutation or the same allele for that allele to exist in the population or be expressed. So number 8 here is really an irrelevant question, unless you're trying to understand or determine what MackQuigley actually knows. To ask that question, he either doesn't know what he's talking about, or he's trying to be sneaky. I think I go for the former. Okay. Let's continue on. We have number 9. Number of times mutation must occur to reach new species. I think he's asking about speciation here. It's not a really well-worded question. So I'm going to assume he's asking about speciation, and then speak to that. Now the truth is, speciation doesn't require mutation. The founder effect can cause speciation within a population. So no mutation is needed when you have the founder effect causing speciation. There are several different types of speciation events. Some of them will occur through additions of mutations in the genome. Most of them do not. They work on the genetic availability there. So again, this is another question that points to perhaps a little bit of his ignorance towards evolution and genetics, and really is an irrelevant question, but I'm trying to answer all of these either by restating them in such a way that they actually make sense, or by answering them if they actually do make sense.